Okay, what we're going to do in this video is introduce the Paremus Service Fabric 1.14 release and demonstrate its applicability for both traditional cloud compute but also edge and fog compute type environments. Before we actually go into the demo, we'll just set the scene with some background slides just on some of the issues we're trying to address. We'd suggest that the industry today has a fundamental problem, a problem in the way that we're trying to build pervasive distributed software systems. This problem is a fundamental roadblock for some of the aspirations of Smart City and Industry 4 that we'd like to achieve over the next decade. So what is this problem? Quite simply, complexity. The software systems we're building are too operationally complex to be sustainable. Operational complexity affects the stability of systems, the reliability, the cost of maintaining them, and just generally adapting and changing them over time. It's not just something that we believe is a problem. A recent survey of CIOs and organizations stated that 93% of them had said that IT complexity had increased, and that one of the main contributors to this was cloud computing, which may surprise some of you, but is really no surprise if you think that what we've been doing with cloud computing, virtualization, containerization is inserting more and more layers of indirection between the application and the actual physical infrastructure upon which it runs. That all increases complexity, and if it's not managed correctly, if it's not abstracted correctly, it can cause, it is causing a lot of problems in the industry. So we have a complexity crisis. It's a pervasive problem. It's faced by every enterprise. The larger enterprises get away with it by simply throwing high-skilled IT staff at the problem. But this is a fundamental roadblock for smart cities and Industry 4. These environments are orders of magnitude more sophisticated than enterprise environments. Compute needs to be in situ. It needs to be co-located within the city environment or within the manufacturing facility. In smart city environments, there may be thousands, hundreds of thousands, or millions of devices feeding into a complex and interrelated ecosystem, which is changing over time. Citizens' requirements will change over time. Transport systems, monitoring systems will upgrade and evolve over the lifetime of the city, which is many hundreds of years. And yet, these cities have limited funds. They have small IT departments with general purpose IT staff. They're not the ex-Silicon Valley types who have been involved in driving some of the trends over the recent years. The people who are comfortable booting Linux servers, connecting a network up, and ideally, they need to be able to run this sort of infrastructure. And so we need local cloud infrastructure for these sorts of requirements, which is operationally very simple to install, to manage, and scale. It's secure by default, so you don't have to actually set it up in a manner where it is default. You boot it up and it is default because of the way it operates. It's flexible and adaptable and evolvable. It needs to be simple to evolve over time, simple to change to meet new requirements, simple to upgrade, to patch. And finally, it's going to be decoupled from developers, because in these very large federated environments like smart cities, there's not going to be a DevOps team aligned with your transport system and your energy monitoring system. These are going to be third-party solutions which are imported and run, and those third parties are going to be isolated from the runtime systems for security. Support will change over time, and so the DevOps workarounds used by enterprises are just not going to work. Okay, so the Service Fabric is an attempt to address this very problem. It's operationally simple to install, manage, scale, and maintain. It's a runtime that can scale from lightweight cloud edge type environment, so something you may boot across a number of small Raspberry Pis in a local edge point of presence, or you can scale it across your own infrastructure in your data centers, or third-party physical cloud environments. The Fabric can support traditional applications, modular microservices, or other types of application which are far more modular and far more adaptive. Secure by default, by that we mean there's no reliance on external or internal DNS. The discovery mechanisms within the Fabric are peer-to-peer and fully secured, and do not expose service endpoints to the internet. The software governance and provenance of all the software components is known as far as we can determine at all times. It depends on the types of application you're building and deploying to the Fabric, and we'll demonstrate what we mean by that. And the Fabric's built from the ground up, leveraging OSGi, the industry standard for software modularity. Okay, so we've probably all heard this before, sales pitches about how wonderful software is, and this cartoon sort of is very well known in the industry and sort of summarizes things quite nicely, I think. So I guess we need to prove what I'm saying. So what we're going to do in the demonstrations are, first of all, create a service fabric. We're then going to deploy some sort of standard microservice applications to it, and just have a look at those. We're then going to look at ZooKeeper ensembles and consistency and coherent log management, those sorts of things, and at the same time we'll look at labels and contracts. We'll then look at a really modular Java OSGi application, which is an example from the new en route site. We'll look at some horizontal scaling and asynchronous services. We've then got a very simple Cloud Edge example, and then we'll drop back to a discussion on how we do discovery, the importance of structural hierarchy, and we'll pull all the pieces together in a final couple of slides just to sort of give you a view on where we're taking this technology. Okay, so the first thing we're going to do is create a service fabric. What we're going to do is we're going to create this in a AWS cloud environment. So this is a data center type fabric that you would run in your own data center or in a cloud environment. In this case, we're using AWS. So what we need to do is break out from these slides and move over to my desktop. What I have here is here we go, this is better. Come around. I have the Fabric 114 release installed on my desktop, and what I need to do is go to the Ansible directory, and I'm going to create a AWS Fabric. So what we want to do is just look at the template I'm going to use to create this. We have a very simple YAML template, so you probably have never seen YAML configuration simpler than this. The fabric name will be Paremus. We're going to run in region EW West 1. We're going to use instance types T2 large. We're going to have one infra, and we're going to have, let's say, 20 simples. So let's just change this. $20 nodes. Okay, so what I'm now going to do is launch this with an Ansible script, and we'll let this run. Now, this will take about 5 minutes, so we're not going to sit here and watch this tick through. We'll just take a quick pause and then resume once this is completed. Okay, that took about 8 minutes to create the Amazon environment. The script ran through, and we can see here that we've been told where the management endpoint is at this URL. So what I'm going to do is go to this URL, and we'll be greeted by our service fabric. And I'm going to log in with the default account en route. And in here we can see a service fabric consisting of 21 virtual machines that we've just created. Each one of these is a fiber, so a fabric is created out of fibers. And if I drill into one of these, I can see information concerning this fiber. So some stuff to do with the OSGi environment that it's been built out of, but also information about anything it's doing with Docker. I can look at the JVM information, the virtual machine information, and I can tab quickly between the fibers that collectively create this fabric. Okay. So what we'll do is now go back and actually run an application, because that's what we want to do. But before we do that, we'll just set a little bit of context. So let's go back and fire up the slides again. So we've just created a fabric, and a fabric is created out of one or more fibers. A fiber is an OSGi runtime, which can run on a physical machine or within a container. A service fabric can host multiple systems. A system is a distributed composite application. It's something that you want to manage as a unit in your production environment. A system may be composed of one or more system parts, and each system part is isolated within its own runtime environment. So if the system part is a container image, it's placed in its own Docker container. If the system part is an OSGi assembly, it's run within its own framework. System parts may be anything. So they may be lightweight microservices written in any language that you choose to use, or it may be an application like Postgres or Kafka, Spark, etc. And so a system may be composed of a number of system parts. Some of them may be Java OSGi. You may have Python. You may have some sort of database or column store or whatever. The systems can be completely structured in what you need to do for the particular problem you're solving. Okay, so one of the things the fabric does is manage all the dependencies, configuration and interaction. So by this we mean that from the dependencies point of view, when you fire up a system in the fabric, the dependencies are automatically managed. Here we can see that the system is composed of 3 system parts, A, B, C. When it's deployed and started, component C will start first because that has no external dependencies. Once C is running, system part B will start. And then once B is running, system part A will start, and the public service will be made available for the users. And so it doesn't matter how complicated the internal system dependencies are, the fabric will deal with ensuring that they're wired up in the correct order to ensure the correct behaviors in the runtime environment. Okay, configuration point of view, each system part can be configured via convention, i.e. via environment variables. If it's a system part which is configured via API or perhaps via a configuration file on disk, we can deal with that. And of course, if it's a native OSGi component, we use config admin. The final thing to point out here is that the interaction between the system parts is your concern. The fabric is not opinionated. It does not constrain the sorts of technologies you can use. So microservices REST is completely fine if you want to do that. But if you're using Java OSGi, you can use the very lightweight, low latency RPC microservices mechanisms, or you can use eventing or messaging between the components. All of those and any combination of those are supported. Okay, next, the fabric automatically isolates systems and services. So what we mean by this is if we deploy 2 systems into the environment, each one consisting of components A, B, and C, the fabric will avoid cross-wiring between those systems. So component C, its service will never be consumed by component B in the second system. Automatically, the internal services within each system are isolated and are not visible outside that system boundary. This is good from the point of view of obviously ensuring no cross-wiring, but it also means that external parties can't see the internal functions of each business system. Only when you choose to loosen the scoping can you then export one or more services from a system. So you have to explicitly choose to do that. Okay, what we're going to do in the next demo is actually just demonstrate some of these concepts on the fabric we've just created. So what I'm going to do here is I'm going to import a system which is composed of a number of system components. Okay, and I hit the import, and what happens is the fabric's parsing the description, checking it's syntactically okay. It's then caching in all of the artifacts required to assemble this system at runtime. And once this process is finished, it will tell us that the system is available and valid. Okay, so we're valid and it's managed, which means that this is a deployable entity. So if I now hit the deploy button, what happens is the fabric will be negotiating between the available fibers within the environment, finding the most appropriate places for these service components. So we're looking for a site for service A, a site for service B, a site for service C. Now, if we actually go and look at the endpoints, which we've chosen to make visible, we'll see these actually be created, and we'll see that the services are being exported in sequence. So service C is created first because it has no external dependencies. And then given C is now there, we see that B is now started because it has a dependency on C. And finally, service A will be created because it has a dependency on B. There we go. And we can drill into these endpoints, and we can see that this is a rough and ready microservice endpoint, hello world from C, and this is a Python artifact. We can drill into service B, and we can see hello world B, and that's basically concatenated the messages. And then if we go to A, we can see the public facing service, which is nicely rendered. It says hello world Python A, from Python B, from Python C. And so here we've got a chain of microservices, all written in Python, deployed onto the fabric, with two commands, basically an import and then a deploy. Okay, so what we'll do next is we'll demonstrate the isolation behaviors we were talking about. And we'll do that by importing a second system. This second system, basically the same idea. The components are called the same, but one of them has a different implementation. So we'll import this. We'll see that's valid and managed, so we can actually deploy. And again, this is being deployed into the environment. The fabric's looking for the most suitable fibers to host. Okay, and that's now run. So if we go back and look at the systems view, we can see both of these are running. We look at the apps tab, we'll now see the second set of services appear within the, their endpoints appear within this view. So we now have two service Cs, we now have two service Bs, and we'll have a new service A appear. Okay, there we go. Now, if we look at the service A, we'll see this is hello Python, hello Go, hello Python. So this is a different component within the second system, which is actually written in Golang. And this is completely isolated from the first system. So if I go back, clear these down, I can go back to my first system, refresh. That's not picking up anything from the second system, and likewise in the second system, I go through, refresh. That's never going to pick up any components or services from the first system. This is completely isolated. Okay, so that was a very simple example using two systems deployed to the fabric and demonstrating the isolation provided by the fabric for those systems. Now what I'm going to do quickly is just have a look at what's gone on here. We can drill into the fiber, And as we mentioned, this isn't a Java OSGi artifact, it's actually a Python artifact. So how was this dealt with? Well, if we look at the Docker tab, we can see that the fiber actually decided it was going to be a proxy, and it's loaded in Python service container image. And this is what it is managing in this case. Okay. If we want to see the topology of the systems in the environment, we can do this. I can select where's multi-system deployed. We can see multi-systems deployed on these 3 nodes. Okay. Where's the mixed chain deployed? Okay, that's deployed on these 3 nodes. Right, so let's go back and continue with the slides. So the next thing we want to do is talk briefly about target state and consensus. So one of the ideas with the Service Fabric is that we have the runtime world as it really is, so the services and resources that exist out in the runtime environment, be that the cloud we're running on or the data center we're in. And we have the target states, the services that should be there, the systems that should be there. And the target state is stored in a ZooKeeper ensemble for the fabric. And this is automatically created when the fabric is instantiated on the in the runtime environment. So there's a fabric ensemble that we created in the fabric that we've just been looking at. But we should never use that ensemble that we've created as the fabric ensemble for applications. If you use a single ensemble for all the applications that need consensus, you end up coupling them all together. And so should there ever be a problem with that infrastructure service, they impact all the applications. Now, because creating consensus services tend to be quite difficult, people do that. And large organizations that we know and have worked with have very large ZooKeeper ensembles, just one cluster of them, that the whole business globally hang off and provides a global consensus view for every application. That works and it avoids the operational headaches, but of course if someone breaks that, it will take out the whole environment globally, and that's not a good idea. So how do we deal with this? Well, we just make it very easy in the fabric to create ensembles as required. So if you've got, for example, a HDFS environment and you need a ZooKeeper for that, create a dedicated ensemble. If you've got a Kafka message queue infrastructure and you need a separate ensemble for that, create a dedicated ensemble. And so what we're going to do now is go through that process and just show you how simple that is, and also demonstrate the labeling facility in the fabric. Okay, so back to our running fabric environment. And what we're going to do is, first of all, let's stop these examples we've got running, just so we keep things. So that one's now going to stop. There we go. What we're going to do is also stop the second one. So there we go. And we're going to import a new application, which is basically a set of nodes which do lock management between each other. They count down and they use a ZooKeeper service to provide lock management coordination. So this is our ZooKeeper example. Okay, so what I'm going to do is, just as before, we're going to import this. Now we're importing from a repository. The repository would normally be your organizational repository. It can be Nexus or a file system or whatever you want to use. Once we've imported the system from the repository, the fabric's completely decoupled from that repository because everything's been cached, as we've seen before. Okay, so what we're going to do before we deploy this is just have a look at the structure of this example, because there's a couple of things we need to set up. Okay, so the first thing we notice is that we are dependent on an ensemble. So this requires an ensemble called ZK ensemble, example rather. Okay, and then the other thing that we notice here is that we require fibers to have certain labels if they're going to be used. So what we mean is that in this case, for the system part worker, the fibers to be used must be tagged app layer true. If we want to deploy the web viewer to a fiber, the fiber must be tagged web layer is true. We're just using the tags to demonstrate the capability and control the runtime topology layout of this example. But the first thing we'll do is create, first of all, the ZooKeeper ensemble, which needs to be called ZK example here. Okay, so we've got the name. What we're going to do is go back and look at our ensembles view. And in the ensembles view, we can see there's the Paremus ensemble, which is the default ensemble that was created for the fabric. We just have one node here. What we're going to do is create a new one. And I can select fibers in the environment I want to be in this ensemble. We'll create a ensemble of 3 nodes, and I'll create that. Okay, and so what we have now is a ZK ensemble ZooKeeper with a leader and 2 followers. So there we go. I can extend this out to 5 or 7. I can switch over, so I can actually say, no, actually, I'm going to make that an observer, and that's going to force over another node to be leader. But no, let's make this a participant again. So there we go. We've got the leader here now and 2 followers. It's very fluid, very fast, very simple, the sort of thing that is very easy to do from an operational perspective. So now we've got our ensemble running. The other thing, if you remember, what I need to do is create the labels. So if I go to a fiber and create a label very easily, so app layer is true. Okay. I'll create another label on the next fiber along. Okay, and again, next fiber along. Helps if I spell them correctly. And let's have one more. Okay, and if you remember, we also needed a web layer. And to avoid a single point of failure, we'll have a couple of those, which means that the fabric gets a choice of where to place or relocate. And now we're done. So we've created an ensemble, we've tagged the fibers, and so what we can do is we can deploy the application. So the application is now going to look for appropriate fibers within the fabric. It's going to pick the ones which are labeled app layer true and web layer true for deploying the functionality. And that functionality will wire up with the ZooKeeper ensemble that we just created previously. Okay, now we can see the fabrics located several of the sites, and we've deployed both the ZooKeeper web front end and some workers. So what we'll do is go and look now at the front end, the app tab. And here we can see the front end to the application we've just deployed. And what we can do is give it a number, and it's going to start working down from there. Each one of the ZooKeeper workers is acquiring the lock from the ensemble, holding it and then releasing it, and we can see another worker stepping in and taking its turn in this process. There we go. Very simple example, demonstrating a number of Important capabilities. Okay. So next we will look at a truly modular application. So we've been looking at fairly coarse-grained applications deployed to the Fabric, in the sense that the chain link examples were Python and Go. The ZooKeeper one was actually an OSGi, fully OSGi application, but what we'll do now is use one of the examples from the en route site, import that, deploy that, and we'll have a little look around in more detail at the nature of an OSGi application running in the Fabric. And so what we'll do is take the en route example here. Now this is actually a modified example, and I'll describe that once we've imported it. It's a distributed version of the en route example that you will find on the OSGi en route site. It consists of two components. So it consists of a front end web component, and it consists of a separate back end. Rather than using the H2 in-memory database, it's using a remote back end, which is Postgres based. And having said that, I've loaded in the wrong example here. So I need to load in this example. Just do that. We can run them both, but it's nicer to see a distributed version using a backend that persists. Okay, so once this is ready to deploy, we will deploy. And what we'll find is that we have the front end and the back end. The front end is a pure play Java OSGi environment. The back end is a Postgres database, so that is dealt with as a component, container image running in a Docker environment. Now, if we look at the microservices app, we can see that it's composed of a number of fine-grained components. So a system is composed of system parts. A system part may be composed of a number of system part elements if it's OSGi. And each one of these is an assembly. And if we can drill into here, we can see the complete resolution graph for this OSGi service has been created. We can mouse on here and look at the actual bundles and the relationship between them. The red means imported, green means exported in this case. Okay, so that was interesting. We go back and we can look at the system. If we look at the packager components, this is running in the Docker environment, and we can see it's Postgres running on Alpine Linux operating system. And this is just a standard Postgres container image that's been pulled from Docker Hub. We've not modified it in any way, and so here we're using the configuration via convention approach to dealing with this particular artifact. Okay, if we go to the Apps tab, we can see that we've got the application here, and if we click into that, I can say hello world, and that's been persisted in the backend Postgres database. So this is just the logical extension of the OSGi en route example you'll find on the en route site, just done in a way where we've distributed it on the Service Fabric, and we're using the Service Fabric's capabilities to deal with container images to include stateful backend database rather than the embedded H2 that you get on the en route site. Okay, so let's go back again and continue with the slides. So we've had a quick look at the en route example. Oh, one other thing actually, sorry, it's nice to see here, is if we go to the en route example. Okay, so let's look at this chap. So this is the node which is hosting Docker, okay, as we've seen before. If I actually go to the other node that's running the OSGi components, I can look at the declarative services view for these components, which shows you the declarative services which have been created and some information regarding their configurations, etc. So that's quite useful if you're an OSGi developer. And I can also look at the runtime tab, and I can see the information here regarding the HTTP service that was created and the endpoint information. So that's all quite useful. Okay, so we'll go back to the slide again. And next what we're going to do is a very simple IoT edge cloud example. So everything we've been doing so far has been running in AWS and on 20 nodes in that environment remotely. So what I'm going to do now is create a Service Fabric locally on my desktop. So this is where I'm actually working at the moment. And I'll do this by hand. I'm just going to fire up a OSGi framework with the POS shell, which is the shell within the Service Fabric infrastructure environment, and then issue a command to actually turn this into a fiber. Call this district 9. Good film. And the idea here is we're creating a point of presence. It may be a small microcloud in a city environment responsible for running a set of locally attached IoT devices. It may be a dedicated edge cloud in a manufacturing environment that's responsible for controlling and monitoring a small set of manufacturing components. There we go. This is now running on my laptop. I can go to this locally. Let's just see here. There we go. I can log in just as before. So only this time I've just got one node within this environment. And this is a real physical node. It's an actual MacBook in this case. In exactly the same way as before, I can load an application into this environment and deploy it. So let's do that. In this occasion, I'm going to take a IoT demonstration that we've been working on using the Eclipse SensorNact IoT gateway. So I'm going to import this. And now all the components are being cached into my local runtime environment on the laptop. There we go. And again, so once this process is completed, my laptop's completely decoupled from the outside world. That's now done. So I should be able to go in here and deploy this. Again, exactly the same sort of thing we were doing in the Amazon environment. No difference operationally or conceptually in what we're doing. And we can see this is now deployed. Now, I can go to the web page for this. Let's see if we can find this. There we go. We have a light bulb. Now, this light bulb is a surrogate for a physical light bulb. What we've done is plugged in an adapter to the SensorNact so that it's driving the state of a virtual light bulb on this web page. We can see the light bulb's off at the moment. But what I can do is issue a command to the SensorNact agent to turn the light bulb on. There we go. We turn the light bulb on, and I can turn it off again. I send it the off command, And there we go. We have a IoT edge device created on a edge cloud environment, which was pretty easy to do. Okay. So next, let's go back to the slides again and continue. So one of the things with the Service Fabric is that right from the start of the product development, we've been always thinking about how we create self-similar hierarchies, or something which is referred to in research as a Holonic architecture. And the idea is that no matter what scale you're at, the patterns and the behaviors tend to look the same. And the reason for doing this is it's the way that natural systems tend to be built. And so what we've been demonstrating from a fabric perspective is we have fibers, and fibers have internal structures that relate to their OSGi, and fibers connect as proxies controlling local Docker containers. We demonstrated all of that. We group fibers into fabrics. So a fabric is a collection of fibers working together. And then what we can do, and what we've been doing for an EU project we can talk about in a minute, is grouping these these fabrics into a federation. So each one of these is a fabric working together on perhaps owned by a particular organization. And so we've got this hierarchy of structure, which lends itself nicely to the ideas of fog computing or cloud edge environments. Now, one of the important things that enables us to do this is the way that each service fabric does discovery. So when we create a fabric, the fabric fibers are responsible for finding all the other resources and services in their home fabric. And this is done via a viral or epidemic mechanism known as gossip. We start with some well-known initial pair points that all the fibers know and talk to. And via those pair points, they discover everybody else. And convergence is achieved when every fiber in the fabric sees every other fiber. And at that point, the view at each point in the fabric is the same as everywhere else. Okay. Now, what we can do is we can extend this concept to multiple fabrics, where a subset of fibers in each fabric participate in a shared federation gossip cluster and enable resources and services to be optionally visible to that federation cluster. The other thing we can do that we're showing here is we can bridge services between fabrics. So we can allocate several fibers in one fabric and several fibers in a separate fabric to be in the same gossip group. And across that group, we can export services. And the reason for doing this is that it means that services can be exported within the federation between fabrics, but without any reliance on internet infrastructure. So there's no requirement for DNS. And the services can be off PC, it can be messaging or eventing, it can be MQTT. There's no requirement to use HTTP. Okay, so we're going to do a final quick demonstration concerning this area. So we'll go back to our Amazon fabric. And then what we've got here, if we look at the clusters view, we can see that each one of the fibers in the Paremus fabric can see each and every other fiber in the Paremus fabric, as you would expect. So if we drill in, we can see that this fiber has a view of all of the fibers in the fabric, as you would expect. What we'll do is very quickly create a new cluster. We'll call this demo cluster. We may use this for our application that may require peer-to-peer discovery for its own purposes, and we want to separate this out from the infrastructure that the discovery mechanisms the fabric itself is using. So this is going to be a local gossip cluster we're creating, but it could be dedicated to some sort of application that required this. And we'll just add one more node. Okay, so we've got 1, 2, 3, 4, 5 nodes. I need to set an initial peer, so I'll pick one of these to be the initial peer point where all the others talk to. Okay, and we're going to pick a base port that this gossip group's going to use, and we're going to create this new cluster. So here we go. So here's demo cluster. If I go into this demo cluster, I can see that we've got 0, 5 at the moment. So it's looking to find the other fibers within its peer group. And there we go. We can see that the discoveries are being made, and it's rapidly converged to 5 of 5. So each fiber within that new cluster, the demo cluster, is seeing each and every of the participants in that cluster. Okay. Right, so close to the end now. We go back to the slides and pulling all the pieces together. So we've been demonstrating a lot of different sort of pieces of the puzzle. What are we trying to do? Well, one of the things is looking at modular federated smart cities. So here you may have a number of service fabrics, perhaps 1 or 2 controller fabrics that core to the smart city infrastructure, and then smaller fabrics which are responsible for managing various districts and various functions in those districts as part of the overall federated architecture. So in this case, we've got a streetlight system. The streetlights have embedded software, they're non-Java custom protocol, but they're managed, each district's managed by its own district fabric. And we can see here that fabric in District 1 is responsible for the streetlights there, as well as monitoring light levels in that environment. We've got an OSGi custom bridge, which is responsible for bridging and talking to the custom embedded software on each lamp. We've got the local monitoring infrastructure, which may be quite simple, or it may be advanced AI, machine learning type components. And we've got the light controllers locally. The city fabrics up here are responsible for updating and deploying the local behaviors required, and are also receiving back aggregate information from each of the districts. And so that's just one potential sort of scenario. Again, if we look at modular federated manufacturing, we'd have a number of manufacturing facilities, each one with their own robotic assembly infrastructure, all working locally with a local fabric. These are autonomous environments, so if the manufacturing facility was disconnected from the internet or was for any reason under cyber attack, we could just sever the links and the local manufacturing infrastructure would continue. But when everything's working as it should, each local plant can send aggregated reporting information and receive updates from either the ops center, which is part of the organization's own data center infrastructure, or if they're using third-party cloud, from a fabric running in a third-party cloud. The local manufacturing facilities, the services running on the fabrics here, will be responsible for the command and control and orchestration of the various robotic components in the factory. So cyber physical systems and running the orchestration behaviors to coordinate the behaviors across those systems, being the scenario of interest to us. Now, all of these threads pull together in an EU project called Brain IoT. This was awarded late 2017, has been running for 12 months now. And Brain IoT is convergence of those ideas, so a federated modular OSGi runtime environment with the idea of AI, the ability to deploy smart components within that very flexible modular runtime. OSGi is one of the core standards that's being used. The Service Fabric is the runtime platform in the project, but we're also using W3C Web of Things as a mechanism to talk to embedded devices within the use cases. So a couple of slides relating to that. So the first use case that the group are looking at is mission critical smart city infrastructure. The use case is a water utility plant in Spain, La Coruña. And here we're looking at the ability to deploy and update adaptive AI anomaly detection services at the appropriate points within the water processing environment. And it's a very complicated environment with starting from the catchment all the way through the water processing, cleansing, and then distribution into the city. And so this is sort of one of the use cases within the Brain IoT portfolio. The other one is completely different. It concerns a robotics warehouse, and here robots are issued commands to lift and move materials from one place to another. And what Brain IoT wants to achieve here is the ability for the robot to interact with the environment. If the robot comes across a new IoT-enabled device, it will be able to discover that device. And if the drivers aren't loaded in the robot, it will be able to dynamically determine what's required and load those drivers in order to talk to the device that's been found. So the scenario is that the robot needs to pass through a door. The door is IoT enabled, but the robot doesn't have the behaviors loaded up front to negotiate with the door to pass through this. In the Brain IoT environment, that's not a problem. The robot can actually request that it's found something it can't talk to. The environment can make the appropriate decision to instruct it to load the behaviors, and then can orchestrate whether or not the robot should actually pass through the door. So, for example, if it's an emergency fire door, there may be environmental reasons why you don't want the robot to pass through, because the environment sensors are detecting a problem on the other side. So quite complicated orchestration behaviors, but where the environment is dynamically learning and deploying those behaviors in response to real-time changes in the environment. And all this is enabled through the use of the OSGi and the Service Fabric capabilities that we've been walking through. Okay, so that's the end of the 1.14 demonstration. You'll be able to get a download of the Service Fabric from the Paremus site. You can basically do the same sort of thing I've done here today and create Service Fabric running in AWS, just with the Ansible scripts that are included. You can also use the Cloud Formation template in AWS if you have that, and there'll be instructions on the site as to how to do that. And of course, you can also run all of this stuff on your own physical or virtual infrastructure in your own data centers or your laptops. Any questions, send them through to info@paremus.com, and we'd be glad to answer those. Thank you very much for your time.